Hello everybody. So what we're going to be looking at today is the extreme value theorem and absolute extrema. So what this is an application of derivatives. It's kind of our main application of derivatives. It's why you'll care about derivatives in a lot of other classes. Okay, so let's go ahead and get the idea across. So what we need to talk about first of all is probably what is extrema. Okay, so extreme values mean maximums or minimums. So extreme values or extrema are minimums and maximums of the function. Right? And there are two kinds. So there are local extrema So local extrema, those are going to be the minimum and maximum values in a small region. That's not quite right, but what they are is they are, so the minimum, I'll say the highest and lowest values in a small open interval. Small open interval around the point. I'm going to write a definition and then I'll draw a picture, and then I know it doesn't make sense yet, but it will after the picture. Okay, so the highest and lowest values in a small open interval around the point. The definition is like this. We'll say f of x is a local maximum. So remember, local extrema means maximum or minimum. So f of x is a local maximum or minimum. Sorry, I want to change that to f of a. So we're doing this at a. F of a is a local maximum of f of x if f of a is greater than or equal to f of x for, okay, I just changed my mind about the names of the variables here. Sorry. We'll put a c there. You'll see why momentarily. F of c is a local maximum of f of x if f of c is greater than f of x for all x in an interval a to b containing c. All right, there's an equivalent definition for local minimum. So f of c is a local minimum of f of x if f of c is less than or equal to f of x for all x in an interval, just saw I'm missing an L, a to b containing c. All right, now again, I know that those definitions are not necessarily the most obvious of what's going on. So I'll draw a picture and then it'll make perfect sense, I promise. So if I draw just a function, any kind of function, okay, so here I go. So a function. Okay, so there's my y equals f of x. So the idea is simply this. Wherever there's a local maximum, it's just the highest point around it. So like right here, is there any higher point like from in a little interval around there? No, there isn't, right? Like that's like that red dot is the highest value on that curve right there. Okay, so that is a local max. Try again. Aha, got it. So that is a local max. Okay, now it's not the only one though, because over here there's another one that's also a local max. Now the one here, right, the second one I drew is not the highest point overall, right? Not the highest point overall. The overall maximum but if you take a little interval around it, isn't it the highest one around that point? It is, right? And so that's what makes it a local maximum. So any peak is going to be a local maximum. Any kind of peak is a local maximum. Okay, so there's two local maximums. Now a local minimum is the exact same idea, but for a minimum value of a function. So right here, this point is a local minimum. And I'm looking for any other local minimums and I don't see any. Okay, so that's it. So two local maximums and one local minimum, that's what we have on that function that I drew you. Okay, now what are you going to do with that definition that I gave you? Nothing. Okay, what you need to know is what they look like on a graph, okay, and that there may be more than one local maximum and there may be more than one local minimum. Or there could be none. There could be no local maximums and no local minimums. It all depends on the exact function that you're looking at. Okay? But those are the definitions of local extrema. Now, there's another concept called global extrema or absolute extrema, depending on what book gave you your definition. So, our books was referring to the extreme value theorem. Probably they're going to refer to it as absolute extrema. Let me see here. Blah, 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 blah. Yeah, they use absolute. So absolute extrema. So these are the overall global minimum and maximum values of the function. Okay, so definitions. Let's do the definitions. We say f of c is the absolute maximum of f of x if f of c is greater than, so it's the biggest value of f of x for all x, right? So what's the difference? This f of c is greater than f of x for all x, when for the local extrema, it was for all x in an interval. Okay, so that's the difference. No interval here, because it has to be the biggest one overall. And the same thing for the local minimum. So f of c is the local minimum. I said I'll say because technically you could have more than one. They just have to have the same value. So like if you have a point that's like 3,6 and that's an absolute maximum, okay, so x equals 3, y equals 6 is an absolute maximum. Well, there could be another place that also has a y value of 6. So that function value is just as big as the other one. So they're both absolute maximums because they're the same number. Okay, so there could be more than one. So f of c is an absolute minimum. Word's hard. Minimum of f of x if f of c is less than or equal to f of x for all x. Okay, so I'm not going to draw a separate picture. I'm just going to go back to the picture that we already have here. So I have two local maximums and a local minimum. Well, just looking at this, I can see that this right here is actually the absolute maximum, right? Because there's no higher point on this graph. And where would the absolute minimum be? It needs to be the lowest overall function value. But I don't see a lowest overall function value. It's not this. That's definitely not the absolute minimum, because the function's lower right here, right? Like over here, it's also lower over here. So the green dot cannot be an absolute minimum, because it's not the lowest point overall on the graph. And in fact, since this indicates here that the graph keeps going down forever, there is no local minimum. Or sorry, there's no absolute minimum. If it goes down forever, there's no minimum, right? If it keeps going down. So it goes down forever this way. So there is no absolute minimum. Right? You're not guaranteed these things exist. There's just definitions, and if you have a point that satisfies the definitions, then you have an absolute maximum or an absolute minimum, or a local maximum or a local minimum. Okay? So this function just does not have an absolute minimum. Okay? So that's what extrema are. We have absolute and we have local. Okay? Now we're going to have a theorem, and it's the it's the extreme value theorem, and is very useful for us. So, extreme value theorem. You know what? I just wrote it. I'm going to move it down, and I'm going to mention something else first. Sorry. So let me just draw a little picture for you. Just draw a little picture. Happy little clouds, happy little trees. No. All right. So let's take a function. Okay. So there's a function. Now I'm going to take a closed interval here. I'm going to go from here, and I'm going to go to here. Okay, so the function starts here, ends here, and then in between, right? I should have used a different color than red, but I didn't, so we're stuck with red. So look at this piece of the function right here, right? Now we can figure out, actually, you know what? I'm going to move this point. Sorry. Move this point here. All right. And then I'm going to say it keeps going. Okay. So, all right. So let's say we have that piece of the function. Okay. Now, for on that piece of the function, on A to B, we can see where the minimum and maximum are. Right? Where are they? Let's point to them. So, what is the overall minimum value between A and B, right? We're only in this interval. On that interval, the minimum value is right here, right? That's not the overall minimum, but on the interval from A to B, that's the minimum. So on A to B, I'm just going to put this, I'm going to call this, what should I call it? X1. Call it X1. On A to B, f of x has an absolute minimum at x equals x1. Now you might be thinking like, well, didn't you say that the absolute minimum and maximum was the overall highest and lowest values? I did, but if this is our domain, if this is our domain, then when we say absolute minimum, we're only talking about on A to B. So nothing exists outside of that interval. So like I could even come here and just delete anything like that, right? So if I only drew the part between A and B, you would agree that there's an absolute minimum at x1, right? So yeah, even if the function continues on, if we restrict our domain, then we can have an absolute minimum or maximum on that domain. Okay, and we did. Now, is there an absolute maximum? There is. There is an absolute maximum at, and where would the absolute maximum be on A to B? It would be right here, right? Which actually is at B. Okay, so there's an absolute minimum and there's an absolute maximum. Okay, and what we want to notice about this is that if you're on a closed domain, we see that there's two places. I'm going to rewrite this in a second. We see that there's two places where the maximum and minimum could occur. So we can see, we should notice that on a closed interval, and the closed part is important, B, the absolute minimum and maximum could occur at x equals A or x equals B, right? In this case, at A there was nothing, right? That was not the that was not an absolute minimum or maximum at A, but at B there was a maximum, right? It was an absolute maximum. So you could have the maximum and minimum occur at A or B, the endpoints of the interval. Okay, but that's not the only place, right? Because we also have the x1 here that's in the middle of the interval, right? So we should notice that on a closed interval, the absolute max and min could occur at x equals A or x equals B, but the absolute maximum and minimum could also occur inside the interval. Right? Like the x1 in the picture up there. So that's another place where you could have a maximum or minimum. But if it occurs on the inside of the interval, there's a special property that they have to satisfy, right? The maximums and minimums that occur inside the interval have a special property. What's the property? Well, look at x1. What's special about x1? What's special about x1 is that if you drew the tangent line at x1, it would be horizontal, right? And if the tangent line is horizontal, that means that at x1, the slope is 0. Okay? It means the slope is 0. So specifically, the property, it's a little bit more complicated than just that, but the property is that, So inside have a special property. The property is that f prime of x either is 0 or it's undefined at those points. Okay? And so you're just supposed to notice from that picture there that what we can see in this case, it was a horizontal tangent line. The reason we have to say it could be undefined was because if I do this, like if I have a curve that does this, like it's pointy, then like there's a minimum right there. But the minimum is not a place where the derivative is 0. The minimum is a place where actually the function doesn't exist. Okay, so what I wrote here was just ideas. The formal math is what I'm about to write. Okay, so here's the formal math. Definition. X equals c is a critical point. That's the definition, critical point for f of x. If f prime of c, we're talking about c, f prime of c equals 0, or f prime of c is not defined. And I actually need to change this a touch. I said x equals c is a critical point for f of x. You also need that x equals c in the domain of f of x. So the reason I'm writing that, the reason I'm adding this to the definition is because if your function is not continuous at a point, then of course the derivative doesn't exist. Okay, so we only want to talk about points that you could plug into the function. So if it's not, then it's not a critical point. So it has to be in the domain. So that is a critical point. Place where the derivative is 0 or not defined. I can't highlight everything, that's dumb. Okay, so that's a critical point. Now the reason we care is because we're writing this theorem down, which is very important. We're writing down the extreme value theorem now. This is what we were trying to get to. Extreme value theorem. If f of x is continuous on a closed interval, closed is important, right? Closed interval, a to b, so no parentheses, it's got to be square brackets. If it's continuous on a closed interval, a to b, then f of x has an absolute minimum and maximum. I'll say absolute maximum and minimum on AB. Okay, so we talked about how maximums and minimums don't necessarily occur, but in the case where it's a continuous function on a closed interval AB, then it does occur, must happen. Okay, and specifically we can extend this, and so sometimes they include this in the definition, I guess, and sometimes they don't. But so f of x is continuous, f of x has an absolute maximum and minimum on AB, and furthermore, let's see, the absolute max and minimum occur at either, here's your choices for where the maximums could be, at an endpoint of the interval or at a critical point. So either at a critical point of f of x, or choice number 2, at x equals a or x equals b. All right, so what I'm doing there is just formalizing what we talked about up here, right? Like on the picture, we had a maximum at an endpoint, and we had a minimum at a critical point. And those are the only places where you could have them if it's a continuous function on a closed domain. Okay, so you have to pay attention to the requirements of the theorem, but once you do, then this is what it says. All right. So what are the consequences of this? The consequences are it gives us an exact way to find the maximum and minimum on a closed interval. Okay, so this gives us an exact method to find absolute extrema, right? Extrema just means minimums and maximums. Absolute extrema of a continuous function on a closed domain, or in this case, interval a, b. All right? So here are your steps. These are exactly what you need to do. You follow the steps, you get the answer, and then that's it. You go home. So what's the first step? So the first step is we need to find critical points. Find critical points of f that are inside a to b. We don't care if they're outside to a to b. So like if you're trying to find the maximum of a function between 0 and 5, you don't care about a critical point at x equals 10 because it's not in between 0 and 5, okay? So you only care about the ones that are inside your interval. Find critical points of f of x that are inside your interval. How? Very simple. You're simply going to find, I should call that a or something, find f prime of x. So you have to take the derivative, b, set f prime of x equals 0 and solve for x, right? Because f prime of x equals 0 is one of the places where you have a critical point. Find any points in AB where f prime of x is undefined, right? So those are your choices. Like critical points are places where the derivative is 0 or undefined, so you just find all of those places. So step 1, you find all the critical points, okay? Now then what you do is you just make a list of all of the critical points plus x equals a plus x equals b, okay? And what you're going to do with those points is you're just going to plug those x values into the function. So you're going to evaluate f of x at every critical point and x equals a and x equals b. Okay, so every critical point and a and b. And then what you're going to do is that when you do step 2, you're evaluating the function at every point, that the maximum has to be on the list and the minimum has to be on the list, right? Because according to the extreme value theorem, these are the only 2 places where you could have a maximum. It either has to be at a critical point or at A or B. So we've got a list of all of the possible places by the time you get to step 2 here. So you're guaranteed the maximum and minimum are on your list at this point. So all you do once you evaluate the function at every point is the highest function value you find in step 2 is your maximum. From step 2 is the absolute max, and the smallest, or lowest, I'll say, lowest function value is the absolute minimum. All right, and so that right there is a method. Okay, so that's the exact method that we're going to follow, and anytime you're doing an absolute extrema of a function on a closed interval, you want to simply follow those steps. Okay, let's try to do one. So we're going to try to do this. I'm going to say find the absolute max and min of f of x equals 1/3 x cubed minus 1/2 x squared on the interval 0 to 2. There's my problem. Okay, now I came up, that's not what I wanted. Came up with a function here. I think that's it. It did not do what I wanted it to do. Hold on a second. Okay. Downloads, Desmos graph. I think this is it. Here we go. Yeah. Okay. Sorry about that. It's harder than I thought. How do I make this go away now? Come on. Okay. You did not just see the struggle that I had, but while you were staring at a screen that was not changing, I was fighting a battle against the file manager that would not disappear off my screen. Okay. So here's our function. Let me make it slightly bigger here. Hold on. Okay, that was dumb. I thought maybe I could make it somehow line up with the grid that's already there, but I can't. Okay, so this is the function, right? So this is the function right here that we're talking about. So we're trying to find the minimum and maximum between 0 and 2. So just looking at this, right here is where 0 is, and right here is where 2 is, and if you follow the curve, right, we're talking about this section of the graph. All right, so you can even say, like, before we even do any math, you should be able just to go, okay, well, there is the absolute max. Like, how big is it? Well, I mean, it's hard to tell because it's about this high, right? So how big is that? About 0.6 or something? I don't know. Something like that. Doesn't matter. And there's an absolute minimum, which is the lowest point on the graph, and it looks like it's about here. Oops, that is not what I wanted. It looks like it's about here. I can't tell. Like, it could possibly be at 1. I don't even know. But that's where the absolute minimum would be. And that's it, right? So these two values are the ones we're looking for. Now, I put them on the graph so we could see them, but you don't need the graph to solve the problem. I just was putting that there to help this make sense. Okay. Now let's go ahead and do this from the steps here. So first of all, f of x is continuous, right? Let me just get rid of that. F of x is continuous on 0 to 2 because it's a polynomial, and polynomials are just continuous everywhere. So so we can go ahead and solve it with our method. So the extreme value theorem says we have an answer. So the extreme value theorem says we can solve this for sure. All right, so let's go ahead and solve it. So step one, what's step one according to my method? We need to find the critical points. And to find the critical points, we need f prime, and then we're going to set f prime equal to 0. And if necessary, we're going to look for where f prime is undefined. So it all involves f prime, so we need to find that. So we're looking for critical points of f of x. So we need our function. Where's our function? It is 1/3 x cubed minus 1/2 x squared. Okay, so we are going to find f prime. So this is just very straightforward power rule. So we bring the 3 down in front, so we get 3x squared. And then on the other one, we bring the 2 down in front, we get 2x. So I have f prime of x equals just x squared minus x. Okay, so there's my f prime. What am I going to do with f prime? I'm looking for two things. Where is it 0 and where is it undefined, right? Did I call those B and C? Did I make it split that up? I don't remember. Yeah. Set f prime equal to 0. Solve for f. X. So set f prime of x equals 0. So you go 0 equals x squared minus x. Solve for x. Now this is not meant to be an ordeal generally. All you're going to do here is, I can see x squared, I'll rewrite it, x squared minus x. Those both have an x, so factor out an x. So you have x squared, or x times x minus 1. That equals 0. If you have two things equal 0, that says that either 0 equals the first thing or 0 equals the second thing. Well, the first one gives me x equals 0, or on the other one, if I move the 1 over to the other side, I get x equals 1. Okay? So I have, those are two critical points. Both of those are critical points. All right. Part C. Part C is, where is the derivative undefined? Nowhere, right? The derivative is just wherever it is here, right? X squared minus x. That's not undefined anywhere. That's always defined. So, you know, a lot of times that's the case. You don't have anywhere where the derivative is undefined. So you're really, most of the time, just setting the derivative equal to 0. So we did. We set the derivative equal to 0, and we came up with 0 and 1. Okay, that's it. Next step. The next step is we must evaluate f of x at all critical points. I abbreviate that this way usually. And x equals a and x equals b. So what you're going to be doing, well, where are the critical points? The critical points are 0 and 1. Okay? And then a and b, what are a and b? The a and b are the 0 and the 2 from the interval, right? That is a and that is b. So 0 and 2. We already have 0 on our list, so you don't have to do it again. So these are the three values that we have to evaluate our function at. So we need f of 0, f of 1, and f of 2. And make sure you understand this is f, not f prime. Okay, f, not f prime. What's f? F was the original function. So f of x is 1/3 x cubed minus 1/2 x squared. Okay, so evaluate these. F of 0, 1/3 0 cubed minus 1/2 0 squared, that's 0. F of 1, 1/3 times 1 cubed minus 1/2 times 1 squared, that's 1/3 minus 1/2. I'm pretty sure that's negative 1/6. If not, we'll just have it wrong. Then we have 2. 1/3 2 cubed minus 1/2 2 squared. That is 8/3 minus 2, I think. Where is calculator? Hold on. Wheel my chair across the room. Wheel it back. Okay, where are we? Okay, so I'm just going to do this. 8 over 3 minus 4 over 2, blah, 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 2/3. Okay, so there we go. So I've got f of 0 is 0, f of 1 is negative 1/6, f of 2 is 2/3. So then all that's left to do is interpret my answer, because I know that one of these is the maximum and one of them is the minimum. So we know I can say the maximum is 2/3, right? Because 2/3 is the highest value out of 0, negative 1/6, then 2/3. So the maximum is 2/3 at x equals 2. The minimum is, what's the smallest value on the list? Or sorry, lowest value. The lowest value on the list is negative 1/6, right? It's the only negative one. So the minimum is negative 1/6 at x equals 1. And that's my answer. That made a triangle. Of course it did. Why would it not make a triangle? Are you kidding me? Make a rectangle. Thank you. Okay, so the maximum is 2/3 and the minimum is negative 1/6. Now notice the way that I wrote it. I gave you what the maximum value is. The maximum is 2/3. The minimum is negative 1/6. And then I said at x equals 2, at x equals 1. Because they can ask you for either one of those. They can ask you what is the maximum, and they mean 2/3. Or they could say where is the maximum, and they might mean x equals 2. So if you get a problem wrong, it might be because of that kind of thing. All right, let's go back here. Again, we don't need this picture here, but this point must be at 1 comma negative 1/6. And the absolute maximum must be 2 comma, what was the highest value? 2/3? 2/3. Okay, so we found the minimum and maximum. And notice we did not need the picture for it, okay? We just followed the steps and we came up with the numbers, and there you go. All right, let's keep going. Oh, I like this. So just, we did a whole problem here, but they ask you some theory questions too. So here's a question. Which functions and intervals are guaranteed to have an absolute maximum and minimum? Okay, that's not how they word it exactly, like they say by the extreme value theorem, blah, 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 but that's fine. So I'm going to write some functions, and then we'll talk about them. So we got natural log 1 minus x over 0 to 2, if I could write that, 0 to 2. We've got g of x is ln 1 plus x over 0 to 2. We've got h of x is square root x minus 1 over 1 to 4. We have k of x is 1 over square root x minus 1 over 1 to 4, and then they say none, right? So we have I don't know why I did that. I was in my head, I was like, I can make one perfect box, and then I could use the perfect box as like a box to put a check mark in for all of them, but that didn't work because life is hard. All right. Okay, so which functions are guaranteed to have an absolute maximum and minimum by the extreme value theorem, right? Which means basically which functions are continuous on the interval. That's what we're looking at, which are continuous on their AB. That's what we're being asked. Okay, so so first of all, not this one. No. Why not? Because if you put a 2 in there, you'll have ln of negative numbers, right? Like if you put in 2, ln 1 minus 2 is ln negative 1, which is not even defined. Okay, so I don't want to write that. I'll write it this way. F of negative 2. F of 2 does not exist. That's a short way to write it, right? So it's not continuous because it doesn't even exist on the whole interval there. All right, what about the other one? 0 to 2, the next one, g. ln 1 plus x. That's actually fine, right? Because if you put in a 0, you get ln 1. That's okay. Up to 2, you'll have ln 3. So it's just everything between ln 1 and ln 3. That's fine. That's continuous on that interval. So this is guaranteed to have a maximum or minimum. All right. What about h? Again, think about plugging in 1 through 4 in here, right? If you put in a 1, you'll get like square root 1 minus 1, which is 0. That's fine. If you put in the 4, you'll have square root 4 minus 1, which is square root 3. That's fine too, right? Everything in there is also fine, so that's fine. Now what about the next one, k of x? Now k of x is a little bit different because it's the same square root x minus 1, but if you put in a 1, you get to divide by 0, right? 1 over square root 1 minus 1 is 1 over 0, does not exist. So not that one. So only g and h have maximums and minimums guaranteed to exist by the by the extreme value theorem. Okay, so you're just saying which are continuous. So if there's a divide by 0, no. If it's a natural log of a negative, no. Right? That's all you're looking for. Square root of negative, also not allowed. So you're just looking for that. Okay, that's fine. So you have some like that. You have a couple, like we should do a couple more actually just finding the absolute extrema, huh? There's a couple where you identify absolute extrema from a graph, but I think we talked about that already, so I'm not going to talk about it again. Yeah. I'm just looking for another one to solve. You know what? Let's do this. I know you have one question only like this. Well, I think you have one question only like this. But let's say I give you this: f of x equals 20t over t squared plus 7. And I want to know, find the absolute maximum and minimum on, and I don't know what interval it is, so hold on, let me just pick an interval. I need the graph. Okay, so far so good. Can I make that bigger so we can look at it? Okay, let's just say 0 to 9, right? I see 0 and I see 9, so let's do 0 to 9. Okay, so 0 to 9. So we're talking about from here to here. I'm not going to draw over the whole picture like I did last time. So I think you could actually tell before we start some of the stuff, right? Like, where's the absolute minimum between 0 and 9? You should just be able to look at it and say, right there, there's your absolute minimum. Looks like at 0, 0, right? I don't even need to do any math because I have the graph right there. Now, where's the absolute maximum? Highest point between 0 and 9. Well, that is a little bit harder, right? That looks like about right here, right? That's where it is. But, you know, I don't know the x or the y there. I can't tell. They look like fractions or something, right? So we can't find it just by looking at the graph. Now, what is this point at 9? Nothing. Right? That's not a maximum or a minimum. It's not the absolute maximum or minimum anyway. All right, so let's go see if we can do this. So again, it's continuous, right? From 0 to 9, it's continuous. There's no holes or anything from 0 to 9. Actually, there are no holes anywhere, but, you know, in particular, there's no holes between 0 and 9, no jumps, no nothing. So it's fine. So we can apply our method. The extreme value theorem guarantees solutions to exist. So what do we need? We need to find critical points. Find critical points. How do we do it? The way we find critical points is we need the derivative. So f of x is 20t over t squared plus 7. So we need the derivative. So A, find f prime of t. Now, I put t's here instead of x's, actually. I messed that up, right? T's instead of x's, that's fine. You're just doing everything with respect to t then. All your derivatives are with respect to t. Why did I do that? T. Everything's a t. No x's. All right, so find f prime of t. Now we need the quotient rule, right? You don't get to forget everything you know about derivatives. Have to do the quotient rule. So quotient rule. What's the quotient rule say? Quotient rule says you have the f prime g. That's how I'll write it the way I normally write it. I don't know why I was going to write it different. F prime g minus f g prime over g squared. Okay. Now we take the two derivatives, the smaller ones. Here's a derivative, here's a derivative. Do those derivatives, they're easy. Derivative of 20t is 20. T squared plus 7 minus 20t. The derivative of t squared plus 7 is 2t over t squared plus 7 squared. So multiply it out on top. We have 20t squared plus 140 minus 140t squared over t squared plus 7 squared. One more. So we have f prime of t now is, we can add up the 20t squared and the negative 40t squared. And we could have negative 20t squared plus 140 over t squared plus 7 squared. There's my derivative. We did it. All right, part B. Part B, we are going to set this equal to 0. And solve for t. Now, part of the reason I wanted to do this problem for you was I can show you something that hopefully you'll remember afterwards. Guess that's everything, but there we go. So a key here is whenever a fraction equals 0, whenever like a over b equals 0, that means a equals 0. Right? If a fraction is 0, it means the top is 0. So I don't even really think about this. Like, I don't care about the denominator at all here when I'm setting it equal to 0. So I know my next line of work is simply going to be 0 equals negative 20t squared plus 140. I just throw out the denominator completely, because if the top's 0, the whole thing's 0. Right? So you should know that. Let's keep going. So we're trying to solve this for t squared, for t. So I'm going to move the t squared over. So I get 20t squared equals 140. Well, what should I do? Divide both sides by 20, right? I think it's better not to have that. It's easier to see what's going on. Right, so divide both sides by 20. I should do that with a different color is what I should do. Okay, so you end up with t squared equals 7. So you are going to square root both sides and you get t equals plus or minus square root 7. Okay, now we are only interested in numbers that are between 0 and 9. So even though we got a plus or minus square root 7, we don't care about the negative square root 7. So on 0 to 9, the only critical point from this t equals plus square root 7. Not the minus. The minus is negative. It's outside 0 to 9. Okay, so we have that. Now the next thing was we should find places where the derivative is undefined. So spoiler is at nowhere, but I do want to say something about it. Okay, so just like up here where I wrote this, whenever a over b equals 0, a equals 0, right? But for a over b, or no, I don't want to say it that way. I want to say a over b is undefined. A over b is not defined when b equals 0, right? So if you're trying to look for where this is undefined, you would set the denominator equals 0, okay? But this has no solution. Right? You can't make that 0 because it's t squared plus 7, right? It was t squared plus 7 squared. So it's always bigger than 7 squared. It's always bigger than 49, so you can't make it 0. So that has no solution. So we're back to just this being our only critical point. So, all right, what do we have? We got critical points. So now we go move on to the second step. We need to evaluate f at all critical points and a and b. So what do we have to do? We need f of 0, because that's one of the endpoints. Actually, let me put the critical point first. I don't know why. So what's the critical point? Square root 7. So that's our critical point. We also have a. What's a? 0, right? We're between 0 and 9. So b is 9. So those are the ones that we need to evaluate. So the function was 20t over t squared plus 7. So f of square root 7 is 20 square root 7 over square root 7 squared plus 7. So 20 square root 7 over root 7 squared is 7, and 7 plus 7 is 14. So that's 10 over 7 root 7. Okay. F of 0 is 20 times 0 over root 0 squared plus 7. So it's 0 over 7, which is 0. And f of 9 is 20 times 9 over 9 squared plus 7, which is 180 over 81 plus 7, which is 88. And there you go. Now, something you should do, right, for the next step, we have to interpret this. What's the biggest, what's the smallest? So make sure you know how big these are, right? Because I don't know how big 10 over 7 root 7 is off the top of my head, right? So I'm going to punch that into a calculator. 10 times square root 7 over 7 and fraction to decimal, that this is about 3.78. And this one, 180 over 88, is about 2.04. 05 actually, but it doesn't matter. So we're looking at these numbers here because for the next step, we need to know what the biggest and the smallest one is. So we have an absolute max of what's the biggest value. 10 root 7 over 7 at x equals root 7. We have an absolute minimum of what's the smallest value, 0 at x equals 0. And we should be able to scroll up and just verify that this matches what we had on our graph. I mean, it really ought to, right? Everything should match. Will you please make a box? I just want a box. I just want a red box around the answer. I have simple tastes. Okay. So what's the maximum? Okay, 3.78. Let's look at this. Could that be at 3.78? Sure, right? Looks like it's right. And the minimum was at 0, 0. We knew that from the beginning. So this is at square root 7, and then 10 over 7, square root 7. What is square root 7, by the way? So square root 7 is 2.64. So this is about 2.65 actually. So yeah, so everything looks like it matches the graph, right? Of course it should, right? It's math, it's just gonna work. Okay, so that is pretty much that. Oh, okay, sorry, I'm gonna do one more thing for you. One last thing. We're an hour and 5 minutes, it's a lot. But I want to just do one like this because we didn't do any factoring yet. So I'm just going to say find critical points. We're not solving absolute extrema, just find critical points. F of x equals x cubed minus 3x squared minus 6x minus 2. Right? Just so you don't get like bogged down with this and go, oh, it's too hard. It's not too hard. Stop whining. All right, so find critical points. So how do we do it? What are critical points? You take a derivative and it's where the derivative is 0 or undefined. So we're looking for where is the derivative 0 or undefined. That's what we're trying to do. So of course we're just going to take the derivative. Nothing fancy here. This is just power rule, power rule, power rule. So the derivative of x cubed is 3x squared. The derivative of 3x squared is 6x. The derivative of 6x is 6. And the derivative of 2 is 0. So there's my derivative. So we find the derivative. Easy enough. Now, this is defined everywhere, so we don't have to worry about this part, right? We see f prime defined everywhere. Yeah, well, I'll write that later anyway. All right. So what do we do with f prime? Set it equal to 0, right? So we have 0 equals 3x squared minus 6x minus 6. So you have to solve that. Generally, you're just going to factor. And then if you get stuck, use Wolfram Alpha to solve that if you get stuck. You just type in the equation and you'll get the exact answers. Okay, so for us, I would just factor out a 3, x squared minus 2x minus 2, and then I would be looking for numbers that added up to negative 2 and multiplied to 2. It doesn't factor. You can try, but it doesn't factor, I don't think. So you could use a computer. I'm going to use the quadratic formula. That's what you should do if you're doing it by hand. So for the quadratic formula, I'm going to need x equals negative b plus or minus square root b squared minus 4ac over 2a, where we've got our a, no, that's wrong. We have our a out front there, our b right there, and our c right there. So a is 1, b is minus 2, c is also minus 2. Did I? Okay, signs are right. So we go ahead and we just fill this out. So we got negative 2 is 2. B squared is going to be 4 minus 4 a c. That's supposed to be 2a. I don't know why. Yeah, I just wrote 2. 2 times 1. Work that out. We got 2 plus or minus square root. We have 4. What is it? Minus 4 times negative 2. So that's 4 minus 8, which is 4 plus 8 over 2. So I have 2 plus or minus square root 12 over 2. If I'm trying to simplify this, I would rewrite the 12 as 4 times 3. Then I can square root the 4 and get 2 square root 3 over 2, which is 2 over 2 plus or minus 2 root 3 over 2, which is 1 plus or minus root 3. So I get this. Now on the computer, they write your answer like this. On Newton, they list this as 1 plus 1. They list it as 1 plus square root 3 and 1 minus square root 3. So they split it up and they list both of them as your critical points, which is, correct. So that's how you do it. So when you're trying to set something like this equal to 0, you can do it by hand with the quadratic formula, or you could go to Wolfram Alpha, and Wolfram Alpha will tell you those answers quicker. But if you're solving it by hand, this is how you would do it. So you do that, and that's it. I guess technically for part C, you have to consider where is f prime undefined? Nowhere. All right, so our answers are simply the ones that we just found. This is the only critical points. Okay. And that is that. So what do we do? Critical points, absolute extrema. That's what we learned about. Absolute extrema on a closed domain, and what are critical points. Okay, so that's it. Post this for you, and we'll have more lectures coming. Good luck.